In this chapter, we're gonna learn about surface roughness, friction, wear, and lubrication. So we will learn about various surface features such as roughness, texture, and lay. And we're gonna see how we measure surfaces. And also we're gonna learn about nature of friction and how its magnitude changes depending on what type of parameters, and wear and lubrication we will study, and how can we minimize wear, and finally we will look at different types of lubricants and how they are being used in manufacturing processes. So we're gonna deal with the surface structure, and this structure is a distinct entity. It is very different than the bulk itself. It has different properties, and surfaces have oxide layers, work hardened layers, contaminants. So it might be generated with different ways, but at the end the surface will have influence on the integrity of workpieces, tools, dies, and molds. A microscopic view of a part surface reveals its irregularities and imperfections. And upon close examination, it will be seen that a surface of a metal generally consists of several layers. The bulk part, referred to as the substrate, has a grain structure that depends on previous processing of the metal. For example, the metal substrate structure is affected by its chemical composition, the casting process, or any type of deformation operations or heat treatments performed on the material. The exterior of the part is a surface that is anything but straight and smooth. It is when we magnify it, actually the surface has roughness, waviness, flaws, and it has a pattern, direction due to the mechanical process that produced it, such as plastic deformation, work hardening, because the surface experiences those to a greater extent than the bulk. So all these geometric features are called surface structure. And again, it will depend on the processing method that is employed. Then comes the oxide layer. So if you have not processed the metal in an inert environment, like oxygen-free environment, or if it's a noble metal like gold or platinum, then oxide layer forms over worked hardened layer. And we know oxide layer is like ceramics, right? And oxide layer is much harder than the base metal, so it is actually abrasive, just like ceramics. So it will have an influence on friction, wear, lubrication. And each metal has its own unique oxide and oxides, and each of these oxides will have a different behavior, and it is actually complex. Like when oxide forms on aluminum, it is hard, dense, this thick film of aluminum oxide, which is porous, and this protects the substrate from corrosion. And it has its own advantages, like it helps to do coloring of the surfaces, etc. But in this case, its behavior is different than the other oxide forming on other materials. Like iron, when iron forms oxide, it is rust, and which doesn't provide, there is no corrosion protection at all. So as you have seen that, for example, you have seen that different materials have different oxide layers, and each of these oxide layers has different properties. For example, even after you machine a copper material, it will have a shiny surface, but after some time it will develop a copper oxide layer which is a somewhat dull color. And in stainless steel, for example, they developed a protective layer of chromium oxide due to the chromium added into the structure. And this chromium oxide protects steel against corrosion with the mechanism we call passivation. So once this chromium oxide forms, it protects the steel from further corrosion. So there is also likely to be moisture, dirt, gas, adsorbed gases, and contaminants on the surfaces. So above the oxide layer there will be adsorbed gas layer and moisture layer, and above that, finally, the last layer will be the outermost surface of the metal. This will have contaminants like dirt, dust, lubricant residues, cleaning compound residues, all pollutants from environment. So then if we take a look at the illustration, here we are seeing the metal substrate, and on top of it we have like a work hardened layer, and there is an amorphous layer. This amorphous layer is sometimes some materials form that due to the results of polishing. Metals and non-metals can form such an amorphous layer due to the result of polishing. And then there is the oxide layer we have learned, and on top of oxide layer there are adsorbed gases, and on top of that we have contaminants, and some general idea about the thicknesses to be expected for these kind of layers are also given to us in the figure here. Of course, as the figure label says, the thickness of the individual layers depends on both processing conditions and the environment. So it is not something fixed. And also I should mention, this is not valid only for metals. They are also valid for plastics and ceramics. Of course, for plastics and ceramics also, the surface texture depends on the environment and the production technique. So surface integrity describes not only the geometric features of surfaces and their physical and chemical properties, but also their mechanical and metallurgical properties and characteristics. It is an important consideration in all design and manufacturing operations because it will influence the properties of the material, such as the fatigue strength, resistance to corrosion, and service life. Several surface defects caused by and produced during manufacturing can be responsible for inadequate surface integrity. These defects usually are caused by a combination of factors such as existing defects in the raw or original material. Method or methods by which the surface has been produced. Improper control of processing parameters such as excessive stress, temperature, surface deformation. So let's look at the list of the major surface defects found in practice. Cracks. Cracks may be external cracks or internal cracks, and they can be seen with the naked eye, or maybe they are small, we cannot see them with the naked eye. Craters, these are shallow depressions. Heat affected zone. This is the portion of a part that has been subjected to thermal cycling without melting, like in some welding operations. Inclusions, we have seen that before. These are non-metallic, very small elements or compounds in the bulk of the material. Intergranular attack. So remember the grains and grain boundaries in the structure of materials. So this is intergranular attack, means weakening of grain boundaries due to corrosion. Okay, so the grain boundaries, remember, have different characteristics than the grain itself, because there is the atoms are more free, they are more reactive, they have more energy. So this creates regions, anodic and cathodic regions within the material itself, may make the material susceptible to corrosion, and the grain boundaries weaken, corrode, and this is the intergranular attack. And there are laps, folds, and seams. These are the surface defects resulting from the overlapping of material during processing. Remember, we have seen laps as a forging defect. And there are metallurgical transformations. These are microstructural changes caused by temperature cycling of the material. It may be like phase transformations, recrystallizations, alloy depletion, decarburization, and resolidification, etc. Pits. Pits are again surface depressions, and this is usually due to external chemical like corrosion, chemical, electrical, or physical attack, or fatigue wear. Residual stresses. These are due to non-uniform deformation or non-uniform temperature distribution in the part. Okay. Not everywhere in the part experiences the same amount of same distribution of stress, and this causes residual stresses within the material. Splatter. This is small, resolidified, molten metal particles deposited on the surface, such as maybe during some welding operations. And there is the last one, surface plastic deformation. This is caused by high stress due to factors such as friction, tool and die, contact geometry with the workpiece, worn tools, processing methods. Okay, so let's look at surface texture. Okay, so regardless of the production technique, all surfaces have their own characteristics, which we refer to as surface texture. Although their description is complex, there are guidelines that have been established for us so we can define a surface texture with measurable quantities. So surface texture is defined by 4 features: roughness, waviness, lay or directionality, flaws or defects. So roughness is small, finely spaced deviations from nominal surface that are determined by the material characteristics and the process that form the surface. It is closely spaced, irregular deviations on a small scale and expressed in terms of its height, width, and distance from each other along the surface. What is waviness? It is defined as the deviations of much larger spacing. It is measured and described in terms of the distance between adjacent crests of the waves. We call it waviness width, and the height between the crests and valleys of the waves, waviness height. Waviness occurs because of work deflection, vibration, heat treatment, and similar factors. Roughness is superimposed on waviness. And lay is the predominant direction or pattern of the surface texture. It is determined by the manufacturing method used to create the surface, usually from the action of a cutting tool. And lay is visible to the naked eye. And flaws or defects, these are random irregularities that occasionally occur on the surface. These include cracks, scratches, inclusions, or similar defects in the surface. So now we can visually see here and understand the terminology we have used to describe the surface texture. You see a flaw here, right? So right there, and we said this is just a defect, like scratch, crack, holes, depression, seams, whatever. There is the flaw. And remember, lay is the predominant surface pattern, the direction of it, right? We also call it directionality. So it is, you can see the direction is right this. That is the lay direction. And then there is the roughness. Roughness is this, you can see, right? That is the roughness. And you see the roughness spacing, right? This is the roughness spacing shown here. And there is the roughness height. And then we also learn about waviness. And waviness was deviations of much larger spacing compared to roughness, like this. So here may be like this, right? So this part is the waviness width. Okay, so error of form is general, basically slope of the part. So together, error of form, waviness, roughness, they are forming the surface profile like this. If you combine all of them, see, this comes from the wave, right? And then this comes from roughness, and this slope is from the error of form. Okay. Together they are forming the surface profile. Let's erase this. So in image B, here we are seeing most of the possible lays surface can take, together with the symbol used by a designer to specify them. So here's the different lay symbols you are seeing, and the lay direction here on the surface, and upside down T like this one, and X like this one, and P like pitted, porous, particulate, non-directional lay like this one. So you can read the description. So in this one is lay is parallel to the line representing the surface to which the symbol is applied, and the upside down T is lay perpendicular to the line representing the surface to which the symbol is applied, etc. Surface roughness is generally characterized by two methods. One is arithmetic mean value, RA. The other is root mean square roughness, RQ. In general, we can say surface roughness is defined as the average of the vertical deviations from the nominal surface over a specified surface length. So there are different ways to take this average, right? So there are two techniques here we are learning. So if we take a look at this figure, the blue is the roughness of the surface, right? The nominal surface is being this. Let me get another color. So we are looking at the deviations from this surface over this much length of the part. Of course, these are vertical deviations, right? From the nominal surface, they can be positive and negative, and basically we're gonna average these. So this is the blue is the surface profile. This line here is the center line. Okay. And if we go back and see in the arithmetic mean value, what we do is based on the absolute values of the deviations, we calculate the average roughness given by this equation. So A, B, C, D, you sum them up, and how much of these you divide to n, the length. Okay, so you sum of these lengths. So this one, their absolute value, this sum, this, sum them up and divide it to how many the length, right? The length of the part, or n being the number of deviations included in this length. So let's put here this one is actually this one, right? These are nominal surface. So basically another way to average the surface roughness is using root mean square roughness, basically to in order to overcome these negative values like F, G, H, I. Let's say this side is positive, negative, right? And then they square it, and then they take a root of it. So square root of it, basically it's the square root of the arithmetic mean of the squares of the values, basically. So this is another way to just calculate the roughness value. And there is definition of maximum roughness height, RT, This is the height from the deepest trough to the highest peak. Indicates how much material has to be removed to obtain a smooth surface. So how do we measure surface roughness? There are instruments. If you're interested, you write YouTube surface profilometers and see how it works. So instruments we call surface profilometers. These are, so this profilometer has a diamond tip that travels along a straight line over a surface and periodically records height measurements. And in general, the surface roughness values required for different engineering applications will be different. Here we are seeing how this profilometer works. Here in image A, it is the measuring of surface roughness with a stylus. Here it is going back and forth along the surface, along the workpiece, the surface of the workpiece, measuring and recording the surface roughness. And in image B, we are actually seeing the path of the stylus, the tip of this profilometer. So it is actually, you see the dashed line showing you the stylus path on the surface. You can compare it to the actual roughness profile. Like this is the actual roughness, and this is what it can measure, right? Because of its structure, the tip structure of the stylus. So the shape of it, I mean. So compared to the actual roughness profile, you see the stylus path is smoother. So if you have somewhat smaller stylus diameter and if you have a smoother surface, that is when you get closer to the path of the actual surface profile. And there are other techniques, like microscopes can be used. There's atomic force microscopes that can detect roughness in nanoscale. They have different probes, and so in general, if you look at for different finishing operations, what type of surface profiles they result in, and this is given us from C to F. You see the differences in roughness if you have, depending on what type of finishing operation you have. You have grinding, turning, and lapping finishing operations, some which we couldn't learn. Anyhow, those finishing operations can result in different type of surface roughness values. So this is just to give an idea, depending on the different types of machining or surface finishing, you might end up with different roughness values. Friction plays an important role in manufacturing processes because there is relative motion and friction forces. They are present at tool, die, and workpiece interfaces. And friction, as you can imagine, it dissipates energy, generates heat, which can have detrimental effects. It also impedes free movement at interfaces, like it can influence the flow and the formation of materials in manufacturing processes. But we cannot say friction is not completely undesirable, because there are processes like rolling. So it would be impossible to roll metals without the presence of friction, or in some clamping work pieces on machines. So these all require the presence of friction we have seen in the rolling, right? There have been theories to explain the phenomena of friction. One accepted theory is adhesion theory. So in adhesion theory, it is based on the observation that two clean and dry surfaces, regardless of how smooth they are, contact each other at only a fraction of their apparent contact area. You can see. So in such a situation, the contact load, the N, is supported by asperities, very small projections from the two surfaces in contact with each other. These. So therefore these are small areas, right? So we can and then therefore assume normal stresses at these asperities will be high, because remember the force over area is the stress, and you have small areas that are in contact with. This increases the stresses at these asperities, and this will cause plastic deformation at the junctions, and this will create an adhesive bond, bonding with the plastic deformation. In other words, we can say the asperities form micro welds, tiny regions where welding happens due to plastic deformation. So it takes a certain force to shear the micro weld. The cold pressure welding we have learned is based on this principle, for example. Okay, so another theory of friction is abrasion theory. In this case, it is based on the fact there is a hard surface, such as a tool or die, which penetrates or plows a softer surface, and plowing will cause displacement of the material. In any case, for both theories or both situations, the sliding of two bodies in contact will require a tangential force, and this force is called friction force, as you see in this image here. So the ratio of the tangential force, the friction force F, to the normal force, contact normal force N, is called is the coefficient of friction. This coefficient of friction, it is usually measured experimentally, and it is a very complex parameter. It will depend on many things. So it will depend on the materials, it will depend on the process involved, and it will vary significantly from different manufacturing process to another. Usually in metal working processes, like in cold working, it is like 0.03. So ranging from 0.03 in cold working to 0.7 in hot working. So it is increasing, and in machining operations, it is in between 0.5 to 2. Because their strength is low compared to metals, hard plastics generally possess low frictional characteristics. And that is the reason why this property makes plastics better than metals when it comes to their use as in bearings, gears, seals, and general friction reducing applications, provided that the loads are not high. Because of these, actually, polymers are sometimes described as self-lubricating. And on the other hand, soft plastics like rubbers, they can conform to surfaces, which can lead to high friction. How can we reduce friction? So we need to be careful in terms of selecting the materials that have low adhesion, like carbides and ceramics. Through application of surface films and coatings and use of lubricants such as oil, such as graphite, as a layer between the tool die and the workpiece, again, which minimize adhesion and interaction between two sliding bodies. There is also a way to reduce friction by mechanical ways, which is using ultrasonic vibrations. The amplitude of the vibration can periodically separate the two surfaces, allowing the lubricants to flow freely into the interface. How do we measure friction coefficient? This is, as I said, it is determined experimentally because it depends on many parameters. So what type of two different materials are interacting with each other, right? Do you have a lubricant? Do you have forces? Everything, many parameters will affect the coefficient of friction. So this is determined experimentally, and a widely accepted test is ring compression test. So there is a flat ring is upset, meaning forged, right? The flat ring is upset plastically between two flat surfaces. As its height is reduced, you would expect its height to reduce, right? The ring expands radially outward. This happens because the volume has to stay constant, right? So if the height is reduced, you expect it to expand radially. If the friction at the interface is zero, remember this something we learned, bulging, right? Bulging affects the friction. The friction affects bulging. So as the height is reduced, we said it will expand outward, and it will also experience if there is any friction bulging. But if there is no friction at the interface and both inner and outer diameters of the ring expand as if it were a solid disc. If there is a friction, and with increasing friction, the internal diameter becomes smaller. So let's see that on the actual images here. So the original specimen is shown as number 1, okay? And between two flat dies, we are applying compression of this ring. So if you have a good lubrication or a poor lubrication, you can see the difference in the image A. So remember, if there is poor lubrication, you experience barreling. We have seen that, if you guys remember, in both ways, inner diameter and outer diameter, there will be barreling. With good lubrication, if there is friction is nearly zero at the interface of the sample and the specimen and the dies, then both inner and outer diameters of the ring expand. As you see, this expands and this expands, right? Compared to here the original structure. Okay. And you see the effects of barreling is not even seen clearly. Alright, but if there is a friction, poor lubrication, you see this barreling here, both in the inner and outer diameter. So as we go from number 1 to number 4, the friction is increasing. As you see that the internal diameter is becoming smaller as we increase the friction. So how do we determine the friction coefficient from a ring compression test? So we have information about reduction in height, and we have information about reduction in internal diameter. So based on that, we can read the number of friction coefficient from this chart given to us, which was determined experimentally, and from here I can read my data. Okay, so for example, if there is 40% reduction in height and 10% decrease in internal diameter, right? So it is approximately 0.1 is your coefficient of friction. That is how you read it. Because of wear, parts and components continually have to be replaced or repaired. Wear plates, they are placed in dies where loads are high, and they are important component in some manufacturing operations, and they expect to reduce wear, and these parts can easily be replaced, and it will prevent costly repairs. Well, although wear generally non-desired, so because it can damage the surface, it can damage the surface finish, it also can have beneficial effects. It has a beneficial effect of smoothing and polishing. And you can see this image here, which shows us this smoothing or polishing effect. So A and B, these are surface profiles before they were worn, and after they experience wear. As you can see, the surface became more smoother with wear. So now we're gonna describe basic wear mechanisms relevant to the manufacturing operations. The first one is adhesive wear. So when two bodies are in contact, there is the interface, and if a tangential force is applied, what can take place is shearing. Shearing can take place at the interface of two bodies, like the image you are seeing here. So they're in contact at the asperities, and there's shear. There is a tangential force applied, and this will cause shear at the interface, and or along a path below or above the interface, as you can see. And because of this, because there will be plastic deformation and there will be strain hardening, therefore at the asperities, and there can be diffusion between two bodies, and there can be also mutual solid solubility depending on what type of materials are in contact with. This will create adhesive bonds between these asperity junctions, and these adhesive bonds will be stronger than the base metals themselves. And during sliding, fracture follows a path in the weaker and softer component. You see the softer component and the harder component, and this fracture will take place usually in the weaker component, and we call this wear fragment. And this fragment is typically attached to the harder component here. This attached wear particle eventually becomes detached during further rubbing at the interface and develops into a loose wear particle. In more severe conditions, like if there are high normal loads or strongly bonded asperities and clean surfaces, this is called severe wear. So at the end, how we can reduce this adhesive wear? You can do one or more of the following techniques. So selecting materials that do not develop strong adhesive bonds. So this you need to be very careful because these can be two different materials, right? You need to be careful. You need to select materials that they are not forming strong adhesive bonds. You can use a harder material as one member of the pair, and you can use materials that oxidizes more readily because this will create a protective film. And you can apply hard coatings or coat with one surface with a softer, hence with a low shear strength, and such as thin silver lead, or you can use an appropriate lubricant. Okay, so there is abrasive wear also. This type of wear is caused by hard, rough surface or a surface containing hard particles sliding across another surface. As a result, microchips are produced as wear particles and leave grooves or scratches on the softer surface. So if we take a look at this now, this is the illustration of abrasive wear in sliding, and you are seeing there is this hard particle sliding across another surface and producing microchips. And abrasive wear resistance of pure metals and ceramics has been found to be directly related to their hardness, and therefore abrasive wear can be reduced by increasing the hardness of materials involved, or also can be reduced by reducing the normal load. Elastomers and rubbers, they resist abrasive wear well because they can deform elastically and then recover when abrasive particles cross paths over their surfaces. The best example is an automobile tire, because we know they are made out of rubbers, and when they constantly in contact with paved road surfaces, which are typically rough and abrasive, they can still last, and even highly hardened steel wheel would not last long under such severe conditions, but tires can do, rubber tires can do. Next is corrosive wear, and also known as oxidation and chemical wear. This is caused by obviously some chemical and electrochemical reactions, because corrosion is electrochemical reaction, right? There's anode, cathode. So caused by chemical and electrochemical reactions between metal surfaces and the environment. And the environment can be corrosive, such as water, seawater, oxygen, acids, chemicals, or atmospheric hydrogen sulfide, sulfur oxide. All these corrosive environment can result in corrosive wear. Think of corrosion like the environment is eating up your material, and your material is dissolving into the environment. Therefore, the fine corrosive products become the wear particles. How can we reduce corrosion? Corrosion can be reduced by selecting materials that will resist environmental attack. We can apply coatings, or we can control the environment if possible. This is usually difficult to control what type of environment the material will be used at. But if possible, you can control the environment or reduce operating temperatures in order to lower the rate of chemical reaction. So corrosion is basically a reaction, chemical reaction, electrochemical, and to reducing the temperature will reduce the rate of the reaction, therefore the rate of the corrosion, and therefore the rate of the corrosion wear. And final type of wear is fatigue, and also called surface fatigue or surface fracture wear. This type of wear is caused when the surfaces are subjected to cycling loading, such as rolling contact in bearings and gears, or in forging operations. So because we also know, if you guys remember what fatigue is basically formation of cracks and their propagation, therefore failure due to cycling loads, like tension, compression. And this is the same as at the surface. That is what happening. There is cycling loading the material is exposed to, and this will form wear particles on the surfaces. Wear particles form through the mechanism of spalling and pitting. Well, thermal fatigue is also another type of fatigue wear. In this case, surface crack is first generated by thermal stress from thermal cycling. So thermal cycling means the material is exposed to changing temperatures, and therefore this will create different expansions, compression regions, and this will create stress in between different regions. That is the thermal stress, and this will create the formation of cracks. So these first cracks are generated, and this thermal cycling happens because we have a cool die, and that is coming in contact repeatedly with hot surfaces. Then once the crack forms, these individual cracks join each other, and the surface begin to spell, or we can say just it break into fragments and small pieces. Phenomena similar to the development of potholes on the roads. And how can we therefore reduce the fatigue wear? We can lower contact stresses, we can reduce thermal cycling, or we can improve the quality of materials by removing impurities, inclusions, or other flows, because they can act as nucleation points to cracks, formation of cracks, and then therefore they will keep propagating under the stress conditions. So how can we reduce friction? Because we know the surfaces of tools, dies, molds, workpieces. How can we reduce friction and wear, right? So we know the surfaces of tools, dies, molds, and workpieces, they are subjected to forces, contact pressures, at different magnitudes. There is going to be relative speed between the parts. They are also exposed to temperatures. So all these parameters are important in the reduction of friction and wear. And besides that, there are lubricants we can use, or we also call them metalworking fluids. There are basically 4 regimes of lubrication of interest in manufacturing operations. The first one is the thick film lubrication. In this case, the two surfaces are separated completely by a film of lubricant. Such films can develop in some regions of the workpiece in high-speed operations, or from using high viscosity lubricants that can become trapped at the die workpiece interfaces. The result is a dull, grainy surface appearance on the workpiece after a forming operation. So, as you remember, in operations such as coining and precision forging, we don't want trapped lubricants. They are undesirable because they prevent the blank from completely filling the die cavity. So, here in this figure, we are seeing the thick film lubrication that can occur in metalworking operations. And there is the thin film lubrication. So here we're seeing in image A, it is the thick film lubrication that can occur in metalworking operations. Another type of possibility is thin film lubrication. This happens as the load increases between the die and the workpiece, and as the speed and viscosity of the metalworking fluid decreases. This makes the lubricant film to become thinner, which is known as thin film lubrication. This condition raises the friction at the interface and results in slight wear. So here you see the thin film lubrication that can be possible in metalworking operations. And there is mixed lubrication. In mixed, also called partial lubrication, a significant portion of the load is carried by the physical contact between asperities of the two contacting surfaces. The rest of the load is carried by the pressurized fluid film trapped in pockets, such as the valleys between asperities. You see the trapped, right? But then a significant portion of the load is carried due to the physical contact between the asperities here. Alright, another type is boundary lubrication. The load is supported by the contacting surfaces that are covered with a boundary film of lubricant, which is a lubricant layer that can be as thin as a single molecule. So you see the film forming at the surfaces. We call this the boundary film of the lubricant. And you see the film is attracted to the metal surfaces, preventing direct metal-to-metal contact of the two bodies. This will reduce the wear. You are seeing direct contact is prevented basically due to the formation of this film. Boundary lubricants typically are natural oils, fats, fatty acids, but this film can break down as a result of high temperatures or just being rubbed off during sliding. If this is the case, deprived of this protective film, then the sliding metal surfaces begin to wear and possibly severely damage the surface. Okay, so what are the functions of lubricants or metal working fluids? First, they reduce the friction. This reducing the friction means it will also reduce energy requirements or any rise in temperature due to friction, right? So in this, also it will reduce wear. It will improve material flow in tools, dies, and molds. It will act as a thermal barrier between the workpiece and its tool and die surfaces, thus preventing workpiece cooling or thermal cycling in hot working operations. It can act as a release or parting agent that will help us in the removal or ejection of the parts from dies and molds. Several types of metal working fluids are available, all with different chemistries, properties, and characteristics that could fulfill these functions of metal working fluids. The first one is oils. Oils maintain high film strength on surfaces, as can be observed when trying to clean an oily surface. They are effective in reducing friction and wear, but oils can have low thermal conductivity and low specific heat. Therefore, they don't effectively conduct the heat away that is generated due to friction or plastic deformation during the process. Moreover, it is difficult and costly to remove oils from component surfaces that might be later need to be painted or welded, because we remember those require clean surfaces, right? And it is difficult to dispose them also. So the sources of oils are like mineral oils, animal, vegetable oils, they are possible. Another type of working fluid, metal working fluid, is emulsions. These are a mixture of two immiscible liquids such as oil and water in various proportions along with some additives. Because of the presence of water, the water gives them a high cooling capacity. They are effective, therefore, particularly in high-speed machining operations, where there is a severe temperature rise, which can have detrimental effects on tool life, surface integrity of workpieces, and dimensional accuracy of the parts that is being machined. Another type here we are seeing synthetic solutions. They are just chemical fluids that contain or inorganic or other chemicals dissolved in water. They don't contain mineral oils. So the chemical agents that are added to achieve certain properties, basically they are added to achieve certain properties. soaps, greases, and waxes. Soaps are like sodium or potassium salts, and they are effective boundary lubricants. The soaps they are effective boundary lubricants, and they can form thick film layers at dye-work interfaces. And greases are solid or semi-solid lubricants. They are highly viscous and adhere well to metal surfaces. That's why they are used extensively in machinery. Waxes might be an animal or plant origin. Compared to grease, waxes are less greasy and are more brittle. They have a limited use in metalworking operations, except as lubricants for copper. Additives. So many times metalworking fluids are usually blended with additives, including oxidation inhibitors, rust preventing agents, wetting agents, or antiseptics. So sulfur, chlorine, phosphorus, these are important additives to oils. There are solid lubricants, and we have seen some of them, learned about some of them, like graphite. Graphite is an effective solid lubricant, especially at elevated temperatures. And there is molybdenum disulfide. This is also a lubricant similar to graphite. And there is also some soft metallic and polymeric films. They have low strength, thin layers of soft metals and polymer coatings. These are used as solid lubricants. Suitable metals include lead, indium, cadmium, tin, and silver. And polymers are polyethylene, polytetrafluoroethylene. These are being used. But their strength is low, right? Therefore, they are limited to use due to this, and especially they cannot be used at elevated temperatures. And glass can also be used as a lubricant. Sometimes we mentioned about it. And this is the glass, because it becomes viscous at elevated temperatures. It can serve as a lubricant. And poor thermal conductivity also makes it attractive, because this way it can act as a thermal barrier between hot surfaces and cool dyes. It is used as a lubricant in usually hot forging and hot extrusion. And lastly, we have conversion coatings. So lubricants may not always adhere well to workpiece surfaces, especially under high stress conditions. So failure to adhere can have detrimental effects, like during forging, extrusion, or wire drawing. So for these applications, the workpiece surfaces are first transformed through a chemical reaction with acids, and this is what we call conversion. Although this reaction leaves a somewhat rough and spongy surface, this surface acts as a carrier for the lubricant. So after the treatment, excess acid is removed, and a liquid lubricant such as a soap is applied. Now it will adhere well to the surface and cannot be scraped off easily. Zinc phosphate conversion coatings are often used on carbon and low alloy steels, or oxalate coatings are used for stainless steels and high temperature alloys. So when selecting metal working fluids for a particular application and workpiece material, you need to consider several factors. First, you need to consider the manufacturing process. It will depend on the process, right? It will depend on the workpiece material. it will depend on the tool or die material. You need to look at the processing parameters because some can handle the forces, some cannot. And you need to look at the compatibility of the fluid with the die and tool materials and the workpiece. We don't want it to react with the material. And surface preparation is required. We want clean surfaces. How do we apply the fluid? This is also important. Or can we easily remove the fluid or clean the workpiece after processing? Because it is very important to be able to easily clean. Otherwise, you are increasing the manufacturing costs. You need a special cleaning techniques to remove the metalworking fluid. And contamination of the fluid by other lubricants. That is also something to think about because it will affect the performance. Storage and maintenance of fluids, treatment of waste lubricant, biological and environmental considerations, and of course costs involved in all of the factors listed above. So cost is also important, right? How are you gonna store them? How are you gonna throw them? How are you gonna make sure it is not damaging to the environment? And all these parameters, besides everything we have listed here, everything will require the thought of costs gonna be involved during manufacturing operations with the use of lubricants. So a lot of costs are coming into play. When we are looking at metalworking fluids, we need to make sure certain things. First, they should not leave any harmful residues that could interfere with the production operations. Okay? And the fluids should not stain or corrode the workpiece and the equipment. Periodic inspection is necessary during manufacturing to detect any deterioration caused by the accumulation of oxides, chips, wear debris, bacterial growth, on general degradation or breakdown due to the temperature and time. Wear particles are particularly important because they can damage the system. So proper inspection and filtering is essential. In summary, what have we learned? We learned about surfaces, their properties. We learned that the surface has a particular shape, roughness, appearance, and properties that is different than the bulk material. And they are exposed to environments and therefore subjected to environmental attack. And the surfaces will come in contact with tools and dies during operations, can affect their service life. And geometric and material properties can affect the properties of friction, wear, fatigue, corrosion, and electrical and thermal conductivity. How do we measure the surface features? We have learned about that. And we learned what type of instruments are being used to measure the surface characteristics. And friction and wear, they are among the most significant factors in processing materials. And we try to understand the theories that is trying to explain this phenomena. So we also learned the type of metalworking fluids, what are they, and when we are selecting metalworking fluids, what should be thinking about and what should be careful about. And with this is the end of this chapter.